How are you today?
I'm good. How are you?
Very good. Thank you. Okay, so do you have any questions or things you'd like me specifically to go over?
Can we go over the one where I think it's like equilibrium,
Okay.
like reactions and like combining the equilibriums to calculate the reaction and like the Kc and PAs and all those.
Okay. So you want to look at if we have two reactions, what we do to them in order to combine them to get to a desired reaction. Something like that. Okay. I actually have an example right here. Okay. So let's say that we have we want this reaction. So it's our desired reaction. So this is what we have, or this is our desired equation, and this is what we're given. Find my, got to bring a calculator. Sorry. And then okay, so those are our two equations that we're given, and we're given Kc values for them. Right over here. And we want to figure out what we need to do to manipulate these, and then what we need to do to manipulate these in order to get to a desired equation. So we can see that this NOBR, this NOBR, we have the correct, we have it on the correct side. We just need to multiply this equation by 2. And then if we look at the other one, we see we have BRCL here and BRCL here. Again, we have a 2 here with the 1 here. So we need to flip this equation and multiply by 2. So for the first one, we just need to flip, or sorry, we just need to multiply by 2. For the second one, we need to flip and multiply by 2. Actually, that's written down here. Okay. So anytime we take an equation and we multiply it by 2, we are going to square our Kc value. So we're going to take this NOBR. So 2 NOBR gas goes to 2 NO gas plus BR2 gas. And then we'll take our Kc 0.110 and we're going to square it. Okay. And then for our second one, we're going to flip it and multiply by 2. So we get BR2 gas plus Cl2 gas goes to 2 BRCl gas. And our Kc, we are going to take it over 1 because we flipped it. And then we're going to square it. Okay. Combining these two, we see we cancel out our BR2. That's the only thing we cancel out. So we're ending up with 2 NOBR gas plus Cl2 gas goes to 2 NO gas plus 2 BRCl gas. And our Kc's will be 0.110 squared times by 1 over 0.375 squared. So when we do this, we take the 0.110 and we square it, we get 0.0121. And then we take 1 divided by 0.375. We get 2.67, and then we'll square that. And this gives us 7.11. And now we'll multiply our 7.11 by our 0.0121. And this gives us a Kc value equal to 0.0860.
Do you not have to worry about, no, like, so units won't matter in this?
Nope, Kc is unitless.
Okay, now I understand this part.
Oh, good.
And then the problems that are dealing with the concentrations and having to, I forgot which unit it was in. But it's the one where you have to plug it in, like
Plugging into your ice table?
No, I understand the ones we did yesterday. I understand those.
Okay.
Oh, the slow step and like the first step reactions.
Are you
So,
talking about
like the elementary steps and then the
so you
rate
want to
limit.
go over another one of those? Let's see if I can
Yes.
find one in here.
Where you have your step 1 and step 2s and whatever.
Mhm.
And rate 1, rate 2s.
Yes, I'm just seeing if I can find a good example. Okay, here we go. I found an example in the book. I just didn't know if I had to look online, which would be a pain. Okay. Okay. This one. So we've got a 3-step process. We have Cl2 gas, A1, -1, goes to 2Cl gas, and this is fast. Then we have step 2, Cl gas, plus CHCl3 gas, goes to HCl gas, plus CCl3 gas, and this is our slow step. And then our last step, Cl gas plus CCl3 gas goes to CCl4. They didn't put a state. Oh my goodness. We're just going to assume that's gas. And that is also a fast step. Okay. Just going to fix it because it looks a little funky. There you go. From here, let's see if we can find if there are any intermediates or catalysts. And then we want our overall reaction. And then we'll go ahead and start going through and solving for some things. So let's just look at our overall real quick. So I'm going to go ahead and highlight anything that gets canceled out. So that's going to get canceled out. That will get canceled out. Everything else looks like it'll stay. So we have Cl2 gas plus CHCl3 gas goes to HCl gas plus CCl4 gas. And that's just probably, since the slow step is a one-way arrow.
If you have that on the step 1 in the product side, the 2Cl, how will that cancel out?
There's 2 steps. So step 2 uses it and step 3.
Oh, okay.
And because it is produced and then consumed, we're going to say that those are intermediates. So the Cl is an intermediate and the CCl3. So both of those are intermediates. And generally our intermediates are gonna be things we can't easily draw a Lewis structure for. Like think about Cl. If we drew Cl, it'd look like this. And that is not correct, or that is not a stable molecule. Usually transition or intermediates are not very stable. Okay, so now we know what our intermediates are. We know our overall reaction. Let's go ahead and start writing our equilibrium for our slow step. Or it's not our equilibrium, sorry. Our rate for our slow step. So it is a bimolecular process. And our rate is equal to K2 Cl CHCl3. And this is what we're going to have to rewrite.
How did you get that? How did you get that rate for that?
You use the reactants for the slow reaction and the K for the slow step.
Okay.
So there's our Cl, and there's our CHCl3 right there, and then our K2 right there.
Okay.
Okay, so now, again, since our Cl is an intermediate, we need to look at where it is produced right here. And we see that it is an equilibrium, and it always will be. We're going to write the rate of the forward reaction of the equilibrium and the rate of the reverse reaction for the equilibrium. So for step one, this is the step that the intermediate was produced in. We're going to write the rate constants, the forward and reverse rate constants. Or sorry, rate expressions. So we have rate is equal to K1 Cl2, and then rate, so that's for our forward step. Our reverse step is K minus 1 Cl squared. And remember, because these are elementary reactions, these are actually what are going on, so we can use stoichiometry when we're writing these. After that, since it's an equilibrium, the rate of the forward is equal to the rate of the reverse. So we're going to set what they are equal to each other. So we're going to set this equal to this, giving us K1 Cl2 equals K minus 1 Cl squared. And then we're going to solve for this so that we can replace this part of our reaction. So I'm going to divide both sides by K to the minus 1. So I get K1 divided by K to the minus 1 equals Cl2, or times Cl2 equals Cl squared. Then I'm going to take the square root of both sides. Right? That'll give me square root of K1 over K to the minus 1. And then Cl2 to the 1/2, which is the same thing as writing a square root. That'll be equal to Cl. The square root will cancel out the square. And then this will go in for that Cl. we write it as rate is equal to K2 square root of K1 over K minus 1 times by CL2 to the 1/2. And then remember, we still have this in there, so we need to put that in there as well. CHCl3.
And that will go into the top equation for the rate.
This will, since we've got everything in terms of reactants, this can now be written as our actual rate equation or expression. So we're going to convert that lowercase r into an uppercase R. We're going to take all of our K values. They're going to combine to just give us K. So this is our K for our overall reaction. And then Cl2 to the 1/2, CHCl3.
Where did you get the CHCl3 from?
It was
Okay.
already in here.
Okay.
So we replaced that in there, but left everything else.
Okay.
And that's us done. That is once we've converted into a regular K and an uppercase rate, we are essentially saying that this is what our rate is. And this is actually not a bad looking one. Some of them can look really messy. But this one looks fine. And you can have half orders for reactants. So its concentration does affect the rate. Did you want to try one more or look at one more?
Yes.
Yeah, the stuff we're doing this week for equilibrium is pretty easy. Okay, let's try another one. So step 1, we have.
And do you only do the previous problem for a slow step?
I'm sorry, what?
The problem we just did, we solved for the slow or like the slow process or step 2.
Yes, yes, it'll always be your slow step. So your slow step is what is determining your rate. Everything else is so fast that it's not going to affect your rate when you change their concentrations. I'm just going to write this out and then we'll talk about it.
Okay.
Okay, so this is our new reaction. We have some gold salts in this. And we're converting from a trimethyl to a single methyl gold phosphide salt. So again, we're going to look through, see what is an intermediate, what is not. So this is produced, then consumed. That would be an intermediate. This is produced, then consumed. That would be an intermediate. This is produced, then consumed, also an intermediate. After all that, we get CH3, 3, AuPH3 goes to C2H6 plus C2H6, let's try again, plus CH3 AuPH3. Okay. So now we take our slow step and rewrite. Oh, that's gonna be fun. Sweet. Okay. So we're gonna take again our slow step, and that's what we're going to write our rate out of. So our rate is equal to K2 CH3 3AU
Why did you use that one?
because that's our slow step.
And it's the reactants, correct?
Yep, it's always a reactant.
Okay.
This one's gonna be complicated. Very nice. Okay. Okay. Now we go to where it was produced at, which is right there. And we're going to rewrite it. So we have our forward rate is equal to K1 CH3 3 AU PH3. And then our reverse is equal to K minus 1 CH3 3 AU times by PH3. Okay, and then we set them equal to each other. K1 CH3 3 AU PH3 is equal to K minus 1 CH3 3 AU, and then our PH3. And then we solve for this species right here. So to find it, there it is. And I'm gonna go a little bit faster. So we have K1 divided by K minus 1, then CH3 3 AU PH3, and it's gonna be divided by PH3. Okay. Now, the issue here is that we have this right here. And now we need to rewrite this one, which is very annoying.
Why do you have to rewrite it?
We have to rewrite this one because this is still an intermediate. I'm just hoping I could find. Something real quick. Oops. Mhm. Do, do, do. Try to make sure we're not doing anything weird in here. Do they not have that one in here? No. Oh, okay, here we go. Huh. Yeah, they did. They left the PH3 in here. I was saying, I don't think you can really rewrite this. Okay, well, they left the PH3 in there. Even though it's an intermediate. Huh. I guess PH3 is not, that's a compound you can actually get. That's real weird. Sorry. Okay, well, this is how they, so this is what they kept it as. So we're gonna keep it like this too. When I give it to you guys, you will not have any issues rewriting it in terms of no intermediates.
Now, would this be a problem on the take home or in class?
That I haven't decided yet.
Okay.
Because it's not technically math, right?
Yeah.
But it is a little complicated and can take some time. So it really depends on where I'm at as far as material for the in-class versus the take-home. If I've got plenty of material for the in-class, then I'll leave this as a take-home. So
Okay.
this is where we would be at for that. Okay.
Do you not have to take the square root or whatever like we did for the last one?
No, the only reason we had to take the square root for the last one is because this part was squared right here.
Okay.
So it's only just so we can get that isolated by itself.
Okay.
But since this is already just one, we're fine.
All right. In step 1, when you have the equilibrium arrows,
Uh-huh.
why is it K1 and then K minus 1, but then in step 2 or in 3, it's just
Because step 2 and step 3 are not equilibrium processes. So they don't have a reverse rate constant.
okay.
The K minus 1 is just the reverse rate constant, or the reverse reactions rate constant.
Okay.
Okay. Is there anything else in particular you would like me to go over?
There's nothing in particular.
Okay. We'll do, just for completion's sake, make sure we hit all the math stuff. Let's try a problem, or let's just work a problem. Let me find one that's not too difficult. I want to make sure I'm not putting in one that's okay, here we go. Okay, here we go. So we've got a mixture of 0.2000 moles of CO2 and 0.1000 moles of H2 and 0.1600 moles of water. And it's all placed in a 2-liter vessel. When we put all these things in there, oh, and it's at 500 Kelvin. When we place it all in there, we get the following equilibrium. Okay. And then we have at equilibrium. I'm actually going to get myself a little bit more in here. At equilibrium. Nope, that's my one. We have a partial pressure of H2O of 3.51 atmospheres. And we want to solve for our Kp and Kc. So we're going to start by solving for our Kp because we're given our partial pressure of water. A little bit more room again, because I want to do my recipe with this. So the first thing we need to do when we approach something like this, we see that we're given partial pressures, which means that we need to solve for partial pressures, or our initial partial pressures, right? So we have our Rice table. And the only thing we have right now is that water will have a partial pressure of 3.51 atmospheres. So we need to figure out our initial concentration, or sorry, partial pressures of CO2, H2, and H2O. To figure that out, we are going to have to use the ideal gas law. So we're going to solve for our, so we've got PV equals nRT, right? We're going to solve for our total pressure. We are given volume. We're given our temperature. We can solve for our moles, and we know what our R value is. So we solve for our moles by adding these moles up together. So our total moles is going to be the equivalent of all the moles added up together. So this mole, and this mole value. We have 0.2000 plus 0.1000 plus 0.1600, which gives us 0.4600 moles. And then we can put that into PV equals nRT. So we're solving for our total pressure. Our volume is at 2 liters. Our N is the total moles, 0.4600 moles. Our R is our regular gas constant, 0.08206. Give myself a little more room. Liters times by atmospheres over moles times by Kelvin. And then our temperature, 500 Kelvin. Okay, so we take our 0.4600 times by 0.08206 times by 500 and then divide by 2 liters, giving us a pressure, our total pressure of 9.4369 atmospheres. And we want it in 4 sig figs, so I'll go ahead and put that there. And then to solve for our partial pressures, we just take our mole fractions times by our total pressure. So our partial pressure of CO2 would be our mole fraction of CO2, which is our moles of CO2 divided by our total moles. So 0.2000 divided by 0.4600 times by 9.437 atmospheres, giving us.
Wait, why did you do that?
Because I'm trying to get my partial pressure of CO2. So remember, partial pressure is equal to our total pressure times by our mole fraction.
Okay.
So I've got my mole fraction, which is this one right here, and then my total pressure, which is what I solved for using the ideal gas law. So I take my 0.2000 divided by 0.4600, and then I multiply it by my total pressure, 9.437, and I get 4.103. So that can go as my initial value right there. And I'm actually going to leave all this unitless, although we do know that this is atmospheres. It just makes it a little bit easier. No, I'm actually going to put a 0 right there. And then my partial pressure of H2 will be equal to my mole fraction of H2, so 0.1000 moles divided by 0.4600 moles times by my pressure, 9.437 atmospheres, giving me 2.052. This is for H2, 2.052 atmospheres. And then the last one would be my H2O. So PH2O is equal to my mole fraction of H2O, 0.1600 moles divided by total moles, 0.4600 moles. And then times by my partial pressure, 9.43, or my total pressure, 9.437 atmospheres. Giving me a value of 3.282 atmospheres. And we see that we start out with no CO, so we put a 0 right there. Okay, so we're going to go in the direction of the thing that hasn't been produced yet. So we don't have any CO. We have to have CO to have an equilibrium. So we're going to shift to the right towards products in order to produce some CO. So do minus X here, minus X plus X plus X. And this gives us 4.103 minus X, 2.052 minus X, X, and then, oops, undo, undo, undo. Can you undo, please? Why won't you undo? Oh, there we go. Okay. And then we do 3.282 plus X, which is equal to that 3.510. Oh, sorry. Oh, I just kept erasing things, didn't I? So this is where we actually have an equation that we can solve for X. So that's where we're going to start. We have 3.282 plus X is equal to 3.510. That means our X is equal to 0.228. So now we can get all of our partial pressures. So our partial pressure of H2O we already have. It's 3.510 atmospheres. Our partial pressure of CO is just X, so it's 0.228 atmospheres. Our partial pressure for CO2 is going to be 4.103 minus X, which is 0.228, giving us 3.875 atmospheres. And then our partial pressure of H2 is equal to 2.052 minus 0.228, giving us 1.824 atmospheres. Okay. From here, we can solve for our Kc since we have all of our, or sorry, Kp. So our Kp is going to be equal to the partial pressure of CO times by the partial pressure of H2O divided by the partial pressure of CO2 times by the partial pressure of H2. And then we just plug and chug. So CO is 0.228. H2O is 3.510. CO2 is 3.875. And then H2 is 1.824. Giving us 0.113 for our Kp. And our Kc, we do Kp is equal to Kc RT delta N. As a note, our delta N, these are all ones right here. So we do 2 here, 2 here. So 2 minus 2 gives us 0. So our Kp, 0.113 is equal to Kc times by RT. So R is 0.08206. And then our T is 500. But it's taken to the 0. Anything we take to the 0, this will just go to 1. Right?
Mhm.
So our KC will equal our KP in this case. Okay. Any questions about any of that?
No.
Wonderful. Well, that kind of covers everything we went over this week, including some stuff we did last week, which is great. We really haven't had a lot of hard stuff yet for chapter 15. It's going to get a little harder on Tuesday.
Oh, awesome.
But yeah, if you have any questions, let me know.
Okay.
And yeah, we'll probably do the same thing we did last test. On Thursday, we'll do another practice test where you guys can work together, ask me questions and all that kind of stuff.
Okay.
If you don't have any questions, I am going to head out to my next class. I hope you have a great weekend. Thank you, ma'am.
Thank you.
Have a great day. Thanks. I figure out how to end. There we go. Bye.